Hi there, welcome back. In this video, we will learn to understand and balance chemical equations. The most important reason for thinking in terms of moles is because moles clarify the amount of substance taking part in the reaction. You cannot compare masses. Mass does not tell you the ratio of the substance reacting, but mole does. Moles allow us to look at large populations of interacting particles rather than grams of material. Let's look at an example. Consider hydrogen reacting with fluorine to produce hydrogen fluoride. If all the gases were weighed, you will have 2.016 grams of hydrogen reacting with 38 grams of fluorine to produce 40.02 grams of hydrogen fluoride. This information tells us that the mass is conserved, which is one of the laws of nature. However, it does not tell us the ratio of hydrogen to fluorine, or fluorine to hydrogen fluoride, or hydrogen to hydrogen fluoride. It was determined that the hydrogen and fluorine reacted in the ratio of 1 to 1. For every hydrogen and every fluorine molecule, twice as much hydrogen fluoride was formed. Let's go ahead and see how this came about. Now, this is a particle model of hydrogen, and here in yellow is a particle model of fluorine, and here we have the particle model of hydrogen fluoride. Now we said 2.016 grams of hydrogen reacted with 38 grams of fluorine to produce 40.02 grams of hydrogen fluoride. If we converted the mass to moles and eventually to particles for each one of these, we will discover that you have 1 mole of hydrogen and 1 mole of fluorine. If you converted the mass of hydrogen fluoride produced, you will discover that the number is 2. So you have 1 mole of hydrogen reacting with 1 mole of fluorine to give you 2 moles of hydrogen fluoride. So we represent this as 1 mole of hydrogen reacting with 1 mole of fluorine to produce 2 moles of hydrogen fluoride. Notice that we do not write the number 1. The numbers that go in front of each of these chemical entities, whether it's an element, atom, or a compound, or a molecule, are called coefficients. So I would say that these numbers are called coefficients. So keep in mind that a chemical equation has to be balanced before we can predict the quantities of products formed by mass mole conversion we learned in the mole concept video. So let's go ahead and practice balancing chemical equations. Let's say you have carbon monoxide reacting with oxygen to produce carbon dioxide. The number of moles of each element on the reactant side must balance the number of moles on the product side. So the number of moles of carbon on the reactant side has to be equal to the number of moles of carbon on the product side. And the number of moles of oxygen collectively on the reactant side has to balance the number of moles of oxygen on the product side. So here we have carbon monoxide and oxygen and making carbon dioxide. Yellow for carbon, red for oxygen. What we notice is that the number of moles of carbon is the same. It's 1 and 1. But we have altogether 3 moles of oxygen on the reactant side and only 2 moles on the product side. So the only way we can bring in extra oxygen to the reactant side is by adding a whole molecule. And I've decided to add an entire carbon monoxide molecule. Now that gave me altogether 4 moles of oxygen now. And I only still have 2, so I am still imbalanced with the oxygen. And at the same time, previously my carbon was balanced, but now by bringing in another carbon monoxide, I imbalanced the carbon as well. So I have to react to my decision and try and put another carbon dioxide on this side. So I now have 2 carbons on both sides and 4 moles of oxygen, and I'm good. That tells me that I need 2 moles of carbon monoxide, 1 mole of oxygen, and 2 moles of carbon dioxide. The one thing I want you to remember, never change the subscript numbers to balance the equation. I want you to pause the video now and think about why you should never change the subscript numbers. Well, I'll tell you. If you do that, you are actually changing the compound. Remember that if you ended up putting a 2 here, it's no longer carbon monoxide, it's carbon dioxide. And that's not what we're talking about. So the only way you can balance the individual atoms is by bringing in the whole molecule that contains the atom that you'd like to balance. Okay, let's go ahead and do one more. The question is, find the coefficients of each of these numbers here when the equation is balanced. So my strategy is to look at all of these atoms and pick the easiest one. I will not pick oxygen because oxygen is in 2 different places. I might pick hydrogen or I might pick carbon. It's a good idea to pick non-oxygen, non-hydrogen atoms first to balance the equation. That's not a general rule, but it usually works. So I see that I have 5 moles of carbon here, and I only have 1 mole of carbon on the product side. So let me try and put 5 here and see what happens. Well, that makes the carbon balance. So in doing so, I now have 10 oxygen atoms here, plus the one here, which gives me altogether 11 oxygen atoms, and I only have 2 here. But let me balance the hydrogen. Because oxygen is in different places, I'm going to save the oxygen till the very last. I have 10 hydrogen here, and I find that if I put 5 here, I'll end up with 10 hydrogen. So I've got 10 hydrogen on the product side, I have 10 hydrogen on the reactant side, I have 5 moles of carbon on the reactant side, I have 5 moles of carbon on the product side, and let's see what's happening with the oxygen. I now have 10 plus 5, that makes 15 oxygen on the product side. It's a good thing I didn't deal with the oxygen before. So I need to put a number here that'll give me 15. And the easiest thing to do with oxygen is just go 15 over 2. And at the end, because you're not allowed to have any fraction moles, all we need to do is take the entire equation and then double it. So our final balanced equation is twice C5H10 plus 15 oxygen gives me 5 moles of carbon dioxide plus 5 moles of water. And we now have the mole ratios. We know that for every 2 moles of C5H10 will react with 15 moles of oxygen to produce 5 moles of carbon dioxide and 5 moles of water. And this mole ratio holds true for any mass amounts of the material. I will do one more, and then I will provide you with some practice problems. So let's go ahead and see what's going on. I have 3 moles of nitrogen, 12 moles of hydrogen here, plus 1 here, that gives me 13 moles of hydrogen. I have 1 mole of sodium, 1 mole of oxygen, well, altogether 5 moles of oxygen and 1 mole of phosphorus. On the product side, I have 3 moles of sodium, 1 mole of phosphorus, 4 plus 1, 5 moles of oxygen, 1 mole of nitrogen, and 3 plus 2, that's 5 moles of hydrogen. So there's a lot of elements to think about, a lot of numbers to think about. I want to make my life easy, and I will pick on one element and deal with that. Let's pick sodium. It seems to be the easiest one. So I have 3 moles of sodium here. Why not try putting 3 moles here, which makes the 3 moles of sodium balanced. Of course, never put a 3 here because that won't be sodium hydroxide anymore. It'll be something else. Okay, in doing so, I changed the oxygen and I changed the hydrogen from my original count. I noticed that the oxygens and hydrogens are in different places, and they're usually more difficult to deal with, so you save it till the very last. The next easy one is phosphorus, and I'm good with phosphorus. They're both 1 mole each on the reactant and the product side. Then I want to deal with the nitrogen. Nitrogen is 3 moles here. I have 1 mole here. Let me try putting 3 here to make sure that my nitrogen is balanced. So I'm good with nitrogen, I'm good with phosphorus, and I'm good with sodium. Now for the difficult ones, which is the hydrogen and the oxygen. Well, unfortunately, hydrogen is in 2 different places and oxygen is in 2 different places. So, on both sides. So, I think I want to do hydrogen first. It doesn't matter which one you do first. So, I have 12 plus 3, 15 hydrogen. On this side, I have 9 so far, and I'm hoping to make 15 because I have 4 3s are 12 plus 3, 15 hydrogens. So 9 plus 6 would give me 15. So since there is 2 here, why don't I try putting 3 here? So then the hydrogen is balanced. 3 times 3 is 9, 3 times 2 is 6, 9 plus 6 is 15. All right, that certainly changed the oxygen again. So my oxygen on the reactant side is 4, and this time it's 4 plus 3 because that 3 means 3 of sodium hydroxide. So we've got 3 oxygens here. So 4 plus 3 is 7 oxygen. Now over here, I have 4 oxygen, and I already have 3 oxygen. Aren't we lucky? So the oxygen's balanced. So we've now balanced this equation. Interpretation of this balanced equation is for every 1 mole of ammonium phosphate, you will require 3 moles of sodium hydroxide, and you will produce 1 mole of sodium phosphate, 3 moles of ammonia, and 3 moles of water. And this mole ratio will never change regardless of what the masses of each are. Now pause your video and try this. As with factoring in Algebra 2, the balancing chemical equation comes with practice, practice, and practice. So please pause your video, try this honestly, and then run the video for the answers. Okay, so I'm going to just put the answers here. This is 2, and this is 2. You'll need 3 water, and 2. You will need 2 sodium hydroxides and 2 water. You will need 6 oxygen, 6 carbon dioxide, and 5 water. You'll need 9 oxygen here and 6 sulfur dioxide. You will need 2 calcium phosphate, 6 silicon dioxide, 10 carbon, just 1, 6, and 10. 3 iron, 4 water, and 4 hydrogen. 6, 16, and 12. All right, thank you very much for listening. This ends this video, and the next video would be using the balanced equation to predict the quantities of products formed, or if you knew how much product you formed or you need to form, you can use balanced equations to predict how much reactants you will need. So look forward to seeing you again in my next video. Goodbye. Thanks for listening.